Imagine a world where firefighters can see through thick smoke to locate deadly hotspots, where pilots are protected from invisible laser attacks, and where your groceries are quickly scanned for signs of spoilage. Sounds like science fiction, right? But all of this is possible today thanks to infrared light detection. But here's the catch though. The materials we currently use have some serious limitations. Silicon, for example, is cheap, but it can detect a wide range of wavelengths. Mercury cadmium telluride works well, but it contains highly toxic and rare elements. And while germanium and indium gallium arsenide are highly effective for infrared detection, their high costs make them impractical for widespread or large-scale use. So how do we find a better solution? That's where my work comes in. Using supercomputers, I analyze a massive database of known materials, searching for a new candidate that's not only effective, but also safe and affordable. Let me walk you through how we're tackling this challenge step by step. It all starts with a pool of 150,000 known materials. To narrow this down, I use data like a material's band gap. That's the energy difference between its valence band and its conduction band. You can think of this like a hurdle that electrons need to jump over in order to conduct electricity. For infrared detection, we need materials with a band gap of less than 0.8 electron volts to absorb the wavelengths of infrared light. Using this criterion, I can quickly filter down this list to just 3,000 candidates in a few seconds. Next, I run rigorous calculations on these 3,000 materials to predict their infrared absorbing properties. This process takes hours on a supercomputer, but it sure is worth it. It helps me identify the most promising candidates with high confidence in their infrared absorbing properties. Once I have a shortlist, I dive deeper into their chemical composition. Are they toxic? Are they affordable? To answer these questions, I pull pricing data from the United States Geological Survey and toxicity data from the Centers for Disease Control and Prevention to assess the cost and safety of each material. After all this analysis, one material stands out: zinc tin arsenide. With a band gap of 0.7 electron volts, it's perfect for infrared light detection, and even better, it's made from zinc and tin, two elements that are far cheaper than the indium and gallium used in current technologies. And while it does contain arsenic, it's made from the much safer arsenic metal rather than the highly toxic fumes of arsine gas. By discovering materials like zinc tin arsenide, we're revolutionizing infrared detection, making it safer, more affordable, and more accessible. From protecting pilots to saving lives in emergencies, the future is looking quite bright. Thank you.